Hey PCalc, this is the third video for lesson 2 of section 1.3. We talked about sine, we talked about cosine, and now we're going to talk about tangent. And I just decided that, instead of making videos for the secant, cosecant, and cotangent, I'm just going to hold off on that and maybe just attach some YouTube videos that briefly explain it. And I think that'll suffice. There's no homework problems where you have to actually graph those other three. So let's do number 37a. Well, before we do that, let's just find the generalized version of tangent. So tangent, maybe looking at the unit circle would be wise again. Tangent's a little different. Tangent is the sine divided by cosine, if you recall that fundamental identity. That idea that if I take 0 divided by 1, that will yield the tangent value that I'm looking for right here. Yeah, so at 0 radians, tangent turns out to be 0. At pi over 2 radians, okay, so we'll just keep skipping them. So every 2 represents a pi over 2 on my graph here. At pi over 2, you get 1 over 0, which is an undefined value. And undefined values are basically asymptotes. So at pi over 2, we put a dashed vertical line to designate nobody is crossing through this x value. In fact, the asymptotic behavior is that the curve will get very, very close to it and hug it all the way down to negative infinity or all the way up to positive infinity. If we keep moving along this pattern, it's going to be 0 over negative 1. And that's going to equal 0. So at pi, tangent is also 0. And then as you can see at 3 pi over 2, it's going to follow that same pattern. It's undefined again, and you are going to have another asymptote. Now that's a pretty solid standard by which we're going by. You go to 0, you go asymptote. 0, asymptote. 0, asymptote. But there's a problem. What the heck is going on in between the asymptote and the 0? Well, this is where we can take our unit circle to one other level. What about the points in between 0 and pi over 2? Specifically pi over 4. Well, at pi over 4, the points are the same. It's root 2 over 2, root 2 over 2. And if you take anything divided by itself, it's 1. So at pi over 4, tangent is equal to 1. So pi over 4 is right between 0 and pi over 2, like you saw right here. And it becomes a 1 unit above. If you go to 3 pi over 4, so 1 pi over 4, 2 pi over 4, 3 pi over 4, it's negative root 2 over 2, positive root 2 over 2. Dividing something by the negative version of itself will give you negative 1. All right, and I could do the thing where I fill in every single gap and then we figure out what the curve is. We did this last year, and you guys saw that the tangent curve fills itself out similarly to that. So then you have that pattern of negative 1, 0, 1, and this is kind of the curve that comes out of that. So that's tangent. I can't leave this graph up here and try to graph the other two tangents because the asymptotes are going to probably overlap in a way that's going to be super confusing. Maybe I can do it with the first one, though. So the first one, all it does is have a 4 out front in front of the tangent. And when we talk about amplitude, we're really talking about distances between like peaks and sort of like I almost think of it as like sea level. So here's my peak, 0 is sea level, and then here's my valley below sea level. The amplitude is the distance between them. This really isn't an amplitude, but it's kind of like an amplitude value. It's the distance between the zeros and sort of the points that we're plotting. At any rate, if you just use the strategy of multiply all the y values by 4, it'll show up pretty clear what your curve's supposed to be. So starting from the middle, 0 times 4 is 0, 1 times 4 is 1, 2, 3, 4, negative 1 times 4 is negative 1, 2, 3, negative 4. So this is what happens when you put a 4 in front of the tangent. It stretches it out really, really far. And it's very difficult to graph. Are the asymptotes the same? Yes, they are. Yeah. And this would represent one period of 4 tangent of x. 2 of them would just be 2 of the curves. Remember, a period or a cycle represents how long it takes to I don't want to use the word cycle to define cycle. It's the amount of time it takes before you get back to the starting point. So the starting point is pretty much an asymptote. And it's interesting, it took 2 pi to get from the start of a sine function to its end. It only takes pi units to get from the start to the finish here. So keep that in mind. Tangent, period of pi. Sine and cosine, period of 2 pi. And again, that's only if we don't have certain things going on inside. Well, I'll show you that when the period gets morphed, it gets changed. That's going to affect sort of like, well, let's just say to be continued. You've seen it before. I'll just leave it at that. Okay, so I would plot some more points and flesh out the curve in another spot. I can do that. You're right here. And there you go. What would it look like if tan has an x minus pi over 4 in the parentheses? Well, what does the minus pi over 4 do? It shifts every point and every asymptote right pi over 4 units. So each of these little blocks, we'll say it represents a pi over 4. You're supposed to start at 0 with a 0 y value. That's now over here. Pi over 4 units shifted right. And there's supposed to be an asymptote, or not an asymptote, but it's supposed to be negative 1, 0, 1, and then an asymptote here and an asymptote here. That negative pi over 4, negative 1 value gets shifted to the right one. The asymptote gets shifted to the right one. This unit gets shifted to the right one. This asymptote gets shifted to the right one. And it doesn't affect the distance between these points, okay? There was an implied 1 in front right here. So, another one. So I don't know. I mean, in some ways there's a simplicity to tangent that's just different from sine and cosine. In other ways, there's like the starting point isn't really the starting point. It's sort of like, here's the first point you plot, and it's kind of stuck right smack dab in the middle of the period. So sometimes that can be confusing, And that's why we make these videos, and that's why we work on this problem set, so that you guys kind of get a better feel for it. All right, that's all I'm going to say about tangent.